Swayam Prabha. Digital India. Educated India.
I welcome you all to lecture number 11 on the topic air compressor. Lecture number 11 and 12 we will be studying about air compressor. In lecture number 11 we will be focusing on single stage air compressor, and in the subsequent next lecture it will be a multi-stage one. So let me see the contents. Before having a look at the contents of the lecture number 11, let's have a quick recap of what we have discussed in lecture number 10, that is the previous lecture. In lecture number 10, we studied about the fourth air standard cycle, that is called Brayton cycle. It is the cycle on which a gas turbine operates. In case of an ideal cycle, the combustion process is replaced by a constant pressure heat addition process, and the exhaust process is replaced by a constant pressure heat rejection process. We have seen the actual cycle, how it deviates from the ideal cycle, and we have derived the air standard efficiency of the Brayton cycle, ideal Brayton cycle. It is 1 minus 1 by pressure ratio power gamma minus 1 by gamma. So we infer that the efficiency of the thermal efficiency of the Brayton cycle, ideal Brayton cycle, depends upon the pressure ratio and the specific heat ratio gamma. We have solved numerical, made a comparison between the ideal cases and the actual cases. Now let us move to the contents of this lecture. Introduction. What are the types of, we will start the lecture with introduction, types of air compressor, then we will see the reciprocating air compressor, the construction, the working principle, derivation of the work of compression without clearance volume and with clearance volume, and some numerical questions. So introduction. So most of the industrial applications, many industrial applications require air at various pressure. It can be low pressure, medium pressure or high pressure. So the devices which are used to handle air and to produce the air at such pressures, it can be a low pressure or a medium pressure or a very high pressure. So the devices which are normally employed are fans, blowers and compressors. Fans are used for very small pressure rise, blowers maybe to a moderate level, and compressors are used for very high pressure applications. So these devices are based on the specific ratio. This is as per the ASTM standard, the specific ratio of devices whose specific ratio are above 1.2, and above, they are classified as compressors. Coming into the categories of compressor, the types of compressor, primarily it is classified into two major types, positive displacement and dynamic one. Under positive displacement we have reciprocating and rotary, and under dynamic, axial and centrifugal. Just a small comparison between the centrifugal and the other one. Generally centrifugal compressors are used for handling large volumetric flow rate. So in the syllabus we would be studying in detail about the reciprocating air compressor, single stage, the derivation of work of compression without clearance volume, with clearance volume. Then in the subsequent class, next class we will be dealing with the multi-stage air compressor, how it reduces the work of compression. So this is the schematic of a reciprocating air compressor. It is a very simple one. So it has got this is the piston, this is the connecting rod, and we have a cylinder. There are two valves are there. One is suction valve, it is like inlet valve, and discharge, this is the discharge valve. So here also we can mark the TDC and BDC. TDC is the top dead center, BDC is the bottom dead center. Suppose if most of the compressors will have a clearance volume, there will not be any design without clearance volume. So the volume of the piston above the volume of the piston above the cylinder, when the piston is at TDC, it is called clearance volume. So, here also we have got clearance volume, that is V suffix C. Then this is called clearance volume, and Vs is the stroke volume or swept volume. When we add clearance volume and swept volume, we get the total volume of the cylinder. Okay. So, what happens, the working is very simple. The air is admitted into the cylinder during the suction stroke, and as the piston moves from TDC to BDC, the air is drawn or admitted inside the cylinder due to the pressure difference. And after the suction stroke is completed, the forward stroke is completed, then the air is compressed by the piston, which is exerting force on the gas or the air, and it raises the pressure and temperature of the working substance, and it is discharged through the discharge valve. This is due to the discharge valve. So, the suction takes place through the suction valve, and the discharge is through the discharge valve, and the cycle continues. So, this is the pressure volume diagram of a reciprocating compressor without clearance volume, So, you can see here, this is the portion, Okay. So, if I have provide some space here, if on the PV diagram, pressure volume diagram, if there is some portion which is left close to the y axis, that indicates the clearance volume, like this diagram. So, you can see here, this is the point number 3 or 4 are not touching the y axis. So, here it indicates the clearance volume. This graph shows the compressor with clearance volume, whereas if you compare the diagram which I explained now with this one, there is no clearance provided. So, there is no clearance volume. Okay. So, now 4 to 1 is suction, 2 to 3 is compression process actually, and 2 to 3 is discharge. So, the cycle is 4 to 1, 1 to 2, 2 to 3 and 3 to 4. Okay. So, first we will be deriving the work of compression for the reciprocating air compressor without considering clearance volume, and next we will be doing the same derivation with clearance. Now, the complete cycle is 4 to 1, 1 to 2, 2 to 3 and again 3 to 4. You know, for a thermodynamic cycle, the initial state and the final state should be the same. So, whether you start from 1 to 2, 2 to 3, 3 to 4, 4 to 1, the initial and the final state should be the same. So, process 4 to 1 is suction, 1 to 2 is compression, Okay. So, PV power n, if n is equal to gamma, it becomes a reversible adiabatic, that is ice. If n is equal to gamma, if n is equal to 1, that is PV equal to constant, the process becomes constant temperature process or isothermal process. Okay. So, if n is equal to gamma, that means PV power 1.4 is equal to constant, that is for a reversible adiabatic process. If n is equal to 1.3, it is any value less than gamma, that is less than 1.4, it is polytropic process. So, here our aim is to find out the power required to drive the compressor, that is work of compression without clearance. So, this is an indicator diagram on the PV pressure volume plot. So, if you see the basics, how to find the work done during the cycle or per cycle is the area under the curve, So, this is the portion, the cycle is 4 to 1, 1 to 2, 2 to 3 and 3 to 4. So, the area between these 3, 2, 4, 1 represents the work done per the cycle, and this is not a regular one. Like if you see from portion 3 to I have extended the y axis, that is A, I have extended the point number 2, that is B, and I have extended the point number 1, that is C. If you see 3 to AB, it is a rectangle, whereas 2BC it is not a regular shape. Okay. So, we have a curved portion also. So, what I am going to do is, I have divided this area into this portion 3 to AB, then 2BC1, then 4 AC, because we should know the area under the curve 3 to 4 1, area under the curve area under the curve 3 to 4, 4 3 to 4, 4 to 1, 1 to 2, 3 to 4, 4 to 1, 1 to 2 and 2 to 3. Only this region, only this region, only this region. Okay. So, there are 3 terms are there. So, first term is P2V2, second term is this portion and this is this one. Okay. So, here if you see this portion, you take this portion 2 3 AB. So, for that 2 3 AB, the work done is P2 into V2. How I got this one is, this is a constant pressure process, these two are constant pressure, 2 to 3 and 4 to 1 are constant pressure. So, P2 equal to P3, P2 is equal to P3 and P4 is equal to P1. So, which you can see from the PV diagram, from PV diagram. So, let me draw this again here, volume pressure, okay. So, this is 4, this is 1, this is the compression process, okay, and this is discharge, this is discharge, this is suction, this is suction, and I extend this line, this is A, this is B and this is C, and I want to find the area under the curve. The cycle is the thermodynamic cycle is 3 4 1 3 4 3 to 4, 4 to 1, 1 to 2 and 2 to 3. This is the cycle. This is the cycle. So, I want to find out the area possessed by this curve. So, this is my work done. This is my work done per cycle. This is work done per cycle. So, further what I am doing is this area plus this area. Okay. So, this is area 3 to A to B, B to 2 plus area under the curve 2 to B, B to C, C to 1, that is this area. So, this area, this entire area plus this area. So, I will get the area under this curve and I will subtract this portion, because I want the work done by the cycle or during the cycle only for the shaded portion. So, this area plus this area and subtract this portion. So, we will get this one. So, area 3AB2 plus area 2BC1 minus 41CA minus area 4 to 1, 1 to C, C to A, sorry 4 to A, let me rewrite it, 4 to A to C and C to 1. So, this portion to be subtracted, this portion to be subtracted. So, that is the work done, work of compression. So, this is equal to, for 3AB2, so this is the pressure at 2 is equal to pressure at 3, because the y axis is pressure. So, it is P into PdV, okay. So, it is PdV, or we can straight away write, because here the volume is V2 here the volume is V2, here the volume is V3, there is no clearance volume, there is no clearance volume in this case which we are considering. So, it is P into V2 minus V3. But what is V3? V3 is 0 because there is no clearance provided here. So, V3 is equal to 0, V3 is equal to 0 because there is no clearance volume. Without clearance, without clearance. So, there is Vc is equal to 0, Vc is equal to 0. Vc equal to 0 means here Vc equal to V3, therefore, since clearance volume equal to 0, therefore, V3 is equal to 0, therefore, this portion the work done, let me write the full terms, then I will substitute, that will be easier, that will be easier. So, this is for this area under the curve 3AB2. Next 2BC2, this is the actual compression process, that is 1 to 2. So, we have taken a polytropic process. So, I will use gamma will be replaced by n, gamma will be replaced by n. So, this is PV power n is equal to constant. So, the work done during a polytropic process from the thermodynamic relation is P2V2 minus P1V1 by n minus 1. So, that is the area for this portion. Okay. So, this is the actual process. So, actually this is for the area 2 to 1. I have taken this portion just for understanding. So, P2V2 minus P1V1 the whole power divided by n minus 1, n minus 1. So, that is the second term. First term it is P into V2 minus V3 and this portion to be subtracted, this portion to be subtracted, this portion to be subtracted. So, that is again minus P1 into V1 minus V4. Now, in this is the area possessed by the curve 3AB2, this is the area possessed by the curve 4AC1, 4AC1. So, this portion to be subtracted, whereas these two portions to be added. So, then only we will get the net, the work done under the curve 4123, 4123. Now, because clearance volume is equal to 0, clearance volume is equal to 0, therefore, volume at 3 and volume at 4 is also 0. Volume at 3 is equal to volume at 4 is because x axis is volume. So, V3 is equal to V4 is equal to Vc is equal to 0, is equal to 0. So, these two terms will get cancelled, that is 0. So, Wc is equal to P into V2, we can take P as P2 because P2 equal to P3, okay. P2 into V2 plus this term there is no change, P2 V2 minus P1 V1 whole power divided by n minus 1 minus P1 into V1, minus P1 into V1. So, this is what I have written here, P2 V2 plus P2 V2 minus P1 V1 by n minus 1 minus P1 V1. Okay. So, in this the derivation is simpler. So, wherever the steps are not very clear or this one, I will write it parallelly. So, take 1 by n minus 1. So, I am taking outside. So, inside P2 V2 minus P1 V1. From this term I am taking this 1 minus term outside. So, let me write it. So, this is equal to 1 by n minus 1 into P2 V2 minus P1 V1. Work of compression is equal to P2 V2. This is for this term, this is for this term. Okay, I have taken n 1 by n minus 1 as this one. I am clubbing these two terms P2 V2 and P1 V1. I am clubbing these two terms. So, plus P2 V2 minus P1 V1, P1 V1. Okay. So, now if you compare these two, P2 V2 minus P1 V1 is a common term. So, P2 V2 minus P1 V1 is a common term. Inside the bracket 1 by n minus 1 plus 1. So, that is what I have written here, 1 by n minus 1 plus 1. Okay. So, take LCM. So, this is equal to P2 V2 minus P1 V1 into n minus 1, n minus 1. So, let us put a, let this bracket be there, n minus 1, 1 plus n minus 1. So, minus 1 and plus 1 will get cancelled, we will get WC is equal to P2 V2 minus P1 V1 into n by n minus 1, n by n minus 1. So, that is what mentioned here, n by n minus 1. So, now you take P1 V1 as a common term. Here if you take P1 V1 outside the bracket, this term does not contain P1 V1. So, P2 V2 divided by P1 V1. Since we have taken this as common term, minus 1 into this term, n by n minus 1. So, that is what equation number 2, this is what equation number 2. Okay. So, this is what equation number 2, this is equation number 1, this is equation number equation 1. So, this will be equation number 2. Okay. So, like for a reversible adiabatic process, we are writing like T2 by T1 is equal to V1 by V2 gamma minus 1, or if it is pressure volume we write gamma. So, like that V2 volume can be written in terms of pressure for a polytropic process. Only thing is gamma is replaced by n, okay. Gamma is replaced by n and n is equal to 1.3 or 1.35 it could be. So, for a polytropic process V2 by V1 equal to P1 by P2. For a polytropic process, 1 to 2, V2 by V1 is equal to P, if it is volume here we have to write pressure, if it is V1 we have to write P2 whole power 1 by n, whole power 1 by n. Okay. So, now since the left hand side is V2 by V1, I can interchange this ratio, I can interchange this numerator and denominator, and in the power I will put a minus sign, it is a very basic mathematics. So, B2 by P1 whole power minus 1 by n. So, this will be equation number 3, this will be equation number 3. So, what I have done is in the numerator within the bracket it is P1 by P2, I have interchanged the numerator and the denominator. So, it has become P2 by P1, sorry there is a small correction here, let me correct it directly. So, here it is P2 by P1, P2 by P1, okay. So, this is P2 by P1. Now, I am going to substitute 3 into this equation 3, I am going to substitute in equation 2, substitute 3 into. So, WC is equal to P1 V1 into, instead of V2 by V1, instead of V2 by V1, see V2 by V1 is this term, instead of V2 by V1 I will substitute this one. So, WC equal to P1 V1 into P2 by P1 into, instead of V2 by V1 I am going to substitute this P2 by P1, P2 by P1 whole power minus 1 by n, and I have minus 1, close the bracket, into n by n minus 1, into n by n minus 1. So, what I have done is I have substituted equation 3 in equation number 2, equation 3 in equation number 2. So, let me write the substituted portion again. WC is equal to P1 V1 into P1 V1 into, let me write the previous equation, P1 V1 into P1 V1 into this term is not there. In the bracket we are having P2 by P1, then I have substituted V2 by V1 as P2 by P1 whole power minus 1 by n, then minus 1, then outside the bracket n by n minus 1, n by n minus 1. So, this is what I have shown here. Okay. Now, you can the base is common here. Here the power is 1, here the power is minus 1 by n. If the base is common, we can add the powers. So, P1 V1 into P2 by P1. Here the power is 1. So, 1 minus 1 by n minus 1 into n by n minus 1. Let me take this n by n minus 1 to the front. Okay. So, n by n minus 1 into P1 V1 into, take LCM, P2 by P1 the whole power n minus 1 by n minus 1. So, that is what we have got here, n by n minus 1. I have taken the n minus term, n by n minus 1 term to the front, P1 V1 into P2 BP whole power n minus 1 by n, this one. So, the equation number 1 is one form of work of compression in case of an air compressor without clearance volume, Now, instead of P1 V1, we can put the equation of state. Okay. So, this will be equation number 4, equation number 4. We know that from equation of state PV equal to MRT. Therefore, P1 V1 is equal to, apply this equation to state 1, P1 V1 equal to M is constant, R is constant, T1. So, now therefore, WC is equal to n by n minus 1 MRT1. The remaining terms will, I will replace only this term, the other terms will remain the same, P2 by P1 whole power n minus 1 by n minus 1 whole power n minus 1 by n. So, this will be equation number 5, So, that is what is equation number 5. Okay. And similarly, we can write the relation between T2 by T1 equal to P2 by P1. If you remember, for a reversible adiabatic process, we have written T2 by T1 is equal to P2 by P1 whole power gamma minus 1 by gamma. This expression I have used while deriving the thermal efficiency of the Brayton cycle in the previous lecture. So, instead of gamma, we are having n for a polytropic process. So, therefore, I am using a similar equation for this one, replacing gamma by n. Therefore, T2 by T1 is equal to P2 by P1 whole power n minus 1 by n. Replace gamma by n. So, I am going to substitute this one here. Therefore, therefore, equation 5 becomes, so substitute this one, equation 5 becomes WC is equal to n by n minus 1 into MRT1 into, instead of P2 by P1 whole power n minus 1 by n, I will write T2 by T1, minus 1. So, this is equation number 6, This is equation number 6. Equation 4, 5 and 6 are various forms of work of compression for a reciprocating air compressor whose clearance volume is 0, that is without clearance volume. Okay. So, the equations 4, 5 and 6 are the work of compression without clearance volume, without clearance volume. So, that brings us to the completion of this derivation. So, that is what I have explained here. Okay. Now, let us derive the similar one for the compressor with clearance volume, So, this is the work of compressor with clearance volume. So, this is the clearance volume. The clearance volume here is V3 equal to Vc, and the swept volume is from V1 to V3. So, this is the swept volume, this is the clearance volume. When we add the clearance volume with the swept volume, we get the total volume of the cylinder, and V1 minus V4, this is the effective swept volume, or the actual volume. volume swept by the piston inside the cylinder, that is in actual operating condition, that is V1 minus V4. V1 minus, it can be referred as an actual volume or an effective swept volume, but swept volume is V1 minus V3, swept volume is V1 minus V3, and let me write it here, Vc is equal to V3, Vs is equal to V1 minus V3, V1 minus V3, and the actual volume is V1 minus V4. So, these three are very important inferences from this pressure volume diagram. So, as we infer from the PV diagram, clearance is provided, that clearance is this portion. Okay. So, similarly, we have to derive the efficiency of the work done of compression, the power required to drive the compressor, reciprocating air compressor with clearance volume. So, it is a very small derivation. Okay. So, WC, this is the equation which you have got, n by n minus 1, n by n minus 1, P2 P1 V1 into P2 by P1 whole power n minus 1 by n minus 1. So, that is what I have written here. Okay. So, let me start here. So, this is equation 7 is nothing but this portion. Equation 4 only I am writing, equation 4 only, okay, I am writing. So, n by n minus 1 P1 V1 into within the bracket P2 by P1 by P1 whole power n minus 1 by n minus 1. So, this is what equation 4, let me see, equation 4, n by n minus 1 into P1 V1 into P2 by P1 whole power n minus 1 by n minus 1, equation 4. Okay. So, this is from equation 4. Since I have used equation 4, 5, 6 for the previous one, I am changing this into equation number 7. Let me follow the same number which is used in the PPT. So, this is nothing but equation number 4, equation 4 and equation 7 are same. Okay. So, now what we are going is, this is equation number 4 is the portion of the equation number 7 is from 4. So, what I am going to do is, this is equation number 7 which I have taken, let me complete the equation right. So, equation 4 is this one. Now, I am going to write the work of compression for the reciprocating air compressor considering the clearance volume, again I am going to take this is the portion 2A B1. So, n by n minus 1 P1 V1 into P2 V1, this is from equation number 4 minus this portion, Okay. So, what we are going to do is, this total, this one minus this portion will give the area under the curve, So, a similar equation I will writing. So, this n by n minus 1 into P1 V1 P2 by P1 whole power n minus 1 by n minus 1 minus, that is for this curve I have written 1 2 AB1 minus this process. This is like an expansion process. This is compression, this is suction, this is compression, this is discharge, this is like an expansion process which follows the law PV power n equal to constant, polytropic process. This is polytropic compression, this is polytropic expansion. So, the first equation is for this compression minus this one. So, that will give the net work done. So, I will write n by n minus 1 P4 V4 into, instead of P2 by P1 P3 by P4 whole power n minus 1 by n minus 1. So, this is equation number 7. The first portion of equation number 7 is nothing but equation number 4, This is what I have written, equation number 4. This is equation number 4. So, let me explain again. So, here clearance is provided, the clearance volume is the Vc, which is nothing but V3, which is nothing but V3. So, first I am writing the equation for the compression process. So, that is already, this is like without clearance, without, this equation is like for without clearance, which we have the n by n minus 1 into P1 V1 P2 by P1 whole power n minus 1 by n minus 1 minus this portion, okay, minus this portion. So, here the, for the initial one I am taking the pressure as P1, for the second one it is P4, of course P1 is equal to P4 and P2 equal to P3. So, the second, this is for the expansion process, this is for the expansion process. Now, okay, now apply this one from PV diagram, P4 is equal to P1, P3 is equal to P2, okay. P4 is equal to P1 and P3 is equal to P2. Let me again emphasize, 4 to 1 is suction, 2 to 3 is discharge, 4 to 1 is suction and 2 to 3 is discharge, 1 to 2 is compression and 3 to 4 is expansion. Okay. So, substitute this one. So, therefore, work of compression is equal to n by n minus 1 into P1 V1 multiplied by P2 by P1. Let us keep the first term as it is, whole power n minus 1 by n minus 1 minus n by n minus 1. Okay. So, instead of P4 you can substitute P1, instead of P4 you can substitute P1, okay, P1 into V4. So, instead of P4 I am going to replace, instead of these terms I am going to replace P4 equal to P1 into V4, within the bracket instead of P3 I am going to write P2, instead of P4 I am going to write P1 whole power n minus 1 by n minus 1. So, this is what I have written here, this is what n by n minus 1 P1 V1, the first term there is no change, minus n by n minus P1 V4 into this one. Now, we can take P2 by P1 whole power n minus 1 by n minus 1 as a common term, this is there. So, we can take, and of course, n is also n by n minus 1 is also say there. So, n by n minus 1 into, okay, n by n minus 1 into. So, take these two terms, because P2 by P1 the term which is inside the square bracket is common. So, let us take this one P2 by P1 whole power n minus 1 by n minus 1 P1 V1 minus P2 P1 V4, okay, okay, and of course, minus 1 will be there, minus 1 will be, that is also there, P2 by P1 n minus 1 by this. So, this is a common term, okay. So, this is equal to n by n minus 1 into P2 by P1 whole power n minus 1 by n minus 1. So, this minus 1 is minus 1. Here you can take P1 as a common term. So, you get V1 minus V4. So, this is what I have written here, V1 minus V4, n by n minus 1 into P1 into V1 minus 1, this term is a common. This is equation number 8, this is equation number 8, okay. And similarly, instead of this term P1 into V1 we can write MRT1, but P1 V1 is equal to M into R into T1, M into R into T1. Therefore, the work of compression is equal to n by n minus 1 into P2 by P1 whole power n minus 1 by n minus 1 into MR T1 into MR T1. So, this will be equation number 9, equation number 9, equation number 9. So, equation number 8 and 9 are the two forms of equation pertaining to work of compression for a reciprocating air compressor with clearance volume, Okay, so equation 8 and 9 are the two forms of work of compression with clearance, So, here the difference is you have got V1 minus V4, V1 minus V4. Okay, so, V1 minus V4, and we know that P1 V1 equal to MRT1. So, we can take that as that is what I have written as MRT1. So, this brings us to the completion of the derivation of the work of compression for a reciprocating air compressor with clearance volume. Okay. So, now let us quickly see some numerical questions based on this single stage compressor. So, I forgot to tell one thing, the single stage, in the single stage compressor we will have only one cylinder where the air is which has been admitted through the suction valve during the suction stroke is compressed, this one in only one stage, that is only by one piston cylinder. We do not have a second cylinder or the third cylinder. So, that is primarily done in case of a multi-stage compression, A single stage, single acting reciprocating compressor with a 30 centimeter bore is the cylinder diameter, and 40 centimeter stroke runs at 400 RPM. The suction pressure and temperature are given 1 bar and 27 degrees. If the delivery pressure is the other name for discharge pressure, 5 bar, find the power required to drive the compressor. So, P1 is given, P1 is 1 bar, P2 is equal to 5 bar. So, the pressure of the air, the working substance is raised from 1 bar to 5 bar. Temperature, initial temperature is 27 degrees centigrade. Temperature is equal to temperature of the air at the inlet of the compressor 27, converted into Kelvin. So, add 273 to Kelvin, and the diameter is given. Cylinder bore is 30 centimeter, stroke is 40 centimeter. Cylinder bore is diameter 30 centimeter, converted into meter 0.3 meter. Stroke is capital L 40 centimeter. Stroke is the distance travelled by the piston between TDC and BDC. It is also called a stroke or it is also called a swept. So, that is why the stroke volume is also called as swept volume. 40 centimeter is 0.4 meter. Okay. So, the RPM is given 400 RPM, 400, N is equal to 400 RPM. Okay. So, it is a very simple this one. You have to find out the power required to drive the compressor. If the process is isothermal, that is PV equal to constant. If the process compression follows the law PV power 1.3, that is PV, it is not 1.4. So, N is equal to 1.3, PV power N equal to constant, that is polytropic process, and if it is reversible adiabatic, that is isentropic. Okay. So, first we should know the volume of air compressed. Okay. So, that is pi by 4 d square into L into N. So, this is a very basic formula. Volume of air compress. Okay. Pi by 4 d square into L into speed, pi by 4. So, pi by 4 d square is the area multiplied by the stroke length will give the volume multiplied by the RPM. So, if you substitute the values, d is given, L is given, N is given. Okay. So, 3.14 square into d square is 0.3. Ensure that the d value and L value are substituted in meter. So, you are getting V1 as 1.188 meter cube per second, 0.188 meter cube per second, and here divide the RPM by 60, we will get revolutions per second. So, we will get in. Okay. So, we have to either you can either you have to convert here RPM into RPS or divide by 60, Here N is in RPM. If you are converting into revolutions per second, no need to divide by 60, So, this is the actual volume of air compressed. Once you know this one, so there are standard formulas, the isothermal work done. isothermal work done. So, isothermal, sorry, let me write the formula. The first one is work of compression for an isothermal process. So, that is very simple formula, P1 V1 into ln of P2 by P1. P1 V1 into ln of P2 by P1. Use this formula, P2 is given, P1 is given. So, whenever there is a pressure ratio, you can substitute in any unit, because the units whether you substitute in bar or kilopascal or Newton per meter square, that is whenever there is a ratio, okay. So, here you substitute, but here this P1 should be substituted in Newton per meter square, P1 should be substituted in Newton per meter square, okay. So, if you calculate the work done, the first process we have been asked to calculate is isothermal. So, that is 30.3 kilowatt. So, substitute the values, you get 30.3 kilowatt. This is the work of compression for an isothermal process. Polytropic process, we have derived just now n by n minus 1 P1 V1 into P2 by P1 whole power n minus 1. So, I will be using that equation. Okay. So, work of compression for a poly. So, work of compression, iso is isothermal, POLY is polytropic process. So, we have to use this equation, n by n minus 1 into P1 V1, okay. N by n minus 1 into P1 V1 into P2 by P1 whole power gamma minus 1 by, sorry, n minus 1 by n, okay, n minus 1 by n minus 1. So, you get the work done during the polytropic process, which is more than the isothermal process work done, 36.7. Here n is equal to 0.3, n is equal to 1.3, okay. So, if you substitute n equal to 1.4, it becomes, n becomes gamma. So, 36.7 kilowatt. So, this is the work done of a polytropic process. So, which is more than the isothermal process. Okay. Next, isentropic. Isentropic is replace n by gamma, and instead of 1.3 we have to substitute 1.4. 1.3 you have to substitute 1.4. So, that is the only change. Third process is isen, that is reversible adiabatic work done. So, that is equal to gamma by gamma minus 1. Let me write it clearly, gamma by gamma minus 1 into P1 V1 into P2 by P1 whole power gamma minus 1 by gamma minus 1. So, the only difference is gamma is equal to 1.4. If it is n, for the given problem n is equal to 1.3, n is given as 1.3. Okay. See here, this is the value of n, this is the value of n, this is the value of n. So, when we calculate the isentropic, the work of compression for an isentropic process is highest among all the three processes. So, 38.5 kilowatt. 38.5 kilowatt. So, for the isothermal process it is least, for the isentropic process or reversible adiabatic process it is the maximum. That is the power consumed by the compressor. If the compressor is following, the compression process is following an isentropic process, then the power consumed is more than the isothermal and polytropic. The polytropic work done is between isothermal work done and isentropic work done. It is more than isothermal work done of 30.3 kilowatt for the example which we have analyzed, but it is less than isentropic work done or reversible adiabatic work done of 38.5 kilowatt. One more question that has been asked, find the isothermal efficiency. So, that is a simple formula. Isothermal efficiency is isothermal, the work of compression in an isothermal process divided by polytropic process, So, isothermal work done is 30.3, polytropic process work done is 36.7, divide, you will get the isothermal work done. So, that I will write it here. isothermal efficiency is equal to work of compression of an isothermal divided by work of compression of a poly. Okay. So, 30.3 divided by 36.7 you get 83 percentage, 82.6 percentage. So, it is a very simple numerical question. So, let us solve one more problem before we wind up. Air at a pressure of 0.98 bar and 20 degree centigrade is compressed to a pressure of 9.8 bar. So, P1 is given as 0.98 bar, P1 is equal to 0.98 bar, P2 is equal to 9.8 bar. So, in the example which we are discussing now, the pressure is increased to 10 times from 0.98 bar to 9.8 bar. It is increased to 10 times. The initial temperature of the air is 20 degree centigrade and the compression follows the law PV power n, PV power 1.2 is equal to constant, that means n is equal to 1.2. So, T1 is equal to 20 degree centigrade, at 273 you will get converted into Kelvin, 293 Kelvin. The compression follows the law 1.2 equal to constant. Compare this with the basic equation PV power n equal to constant. Therefore, n is equal to 1.2, n is equal to 1.2. For the previous problem, it is n equal to 1.3, PV power 1.3 equal to constant. So, find the temperature at the end of compression, find the temperature at the end of compression, that means we have to find out T2, we have to find out T2. So, process 1 to 2, okay, this is a polytropic process. So, T2 by T1 is equal to P2 by P1 whole power n minus 1 by n. So, that is the relation which I used. We know the value of P2, P1, T1 is also given. So, you can find out T2 431 Kelvin. So, T2 equal to 430.7 Kelvin. So, the temperature of the air is increased from 293 Kelvin to 431 Kelvin. So, this is the first part of the question. Okay. Find the temperature at the end of compression, work done per kg of air and heat transfer during compression. Work done per kg of air, we can use the formula, either you can use P1 V1 n by n minus 1 into P1 V1 into P2 by P1 whole power n minus 1 by n minus 1, or we can instead of P1 V1 you can use MRT1 also. You can use either of the equation. So, work done this equal to n by n minus 1 into P1 V1 into P2 by P1 whole power n minus 1 by n minus 1. But V1 is not known, neither it is not given in the question like the previous problem. If the dimensions of the cylinder like the cylinder bore, diameter and the stroke and the RPM are given, we can find V1. So, since it is not given, so instead of this P1 V1 I will use the other equation n by n minus 1 into MRT1, because for R we know the value of R, for air we know the value of R which is 0.287 kilojoule per kg Kelvin. So, I will use this formula. If volume 1 is known, you can use this formula, okay. Because V1 is not known, so I am using this formula n minus 1 by n minus 1. Here if you use this formula, V is unknown, V is not known, V1 is unknown. So, I am using this formula. So, substitute, you will get Wc is equal to 236 kilojoule and m we can assume to be 1 kg. So, 236 kilojoule. And the third question is heat transfer during the compression process. Compression is from process 1 to 2. So, it is mCp delta T. Heat transfer during, I will use the symbol this one, m into Cp into T2 minus T1, simple formula. So, Q substitute the value, Cp is 1.005 for air kilojoule per kg Kelvin, you get around 138 kilojoule, 137.7 kilojoule. So, to summarize, in this lecture number 11, we have seen the construction of a reciprocating air compressor, We have derived the work of compression for two cases. The first one is without clearance volume. The second one is with clearance volume. So, in case of the compressor without clearance volume, V3 is equal to V4 is equal to 0, that is Vg is equal to 0. The total volume of the cylinder is a combination of clearance volume and swept volume. In actual practical applications, all the cylinders will have some clearance this one. So, there will not be any cylinder which has been designed or